Worksheet 5D column buckling. The 4x truss below is made of 2014 aluminum. So they give us the yielding stress 41 KSI and the yaw modulus 10,600 KSI. The truss member have a circular cross section. Circular bar are available in all sizes up to 3 inches in diameter with 1/4 inch increments. What is that about? Go back to lesson 2 where we also design with the incremental diameter or radius or thickness in lesson 2 worksheet. Use the factor of safety with respect to yielding. So 1.5. So you have Fs for yields 1.5 with respect to buckling. So it will be Fs due to buckles it's 4.0. And design the member GF. Design the member GF. That's the member that they want to do. What is the actual factor of safety after design with respect to yielding, with respect to buckling? So basically after you design, select the diameter and then go back to check what is the actual factor of safety. And when you choose when to check the factor of safety that after you design have to be greater than or equal to the given factor of safety. So with the truss, as you can see, this type of problem is similar to the problem we do with the design of the truss member in the worksheet in lesson 2. But this one, the member is in with the buckling. So the member, this one is in compression. The member you learn in worksheet 2 is only in tension. So now compression. So when you learn both, you can apply to design for the whole truss because the truss member is either with internal force have either tension or in compression. So let's go to here. The first part is nothing news to us. We do it a lot in engine mechanics. So the member of interest to design is GF. So let's highlight that is that member that we have here. And as you can see, slope triangle of this one is 2.5 and that is 6. So the other it will be 6.5, right? 6.5 for slope triangle. So that one we first find out the external reaction because that you already know. I don't need to write with the video. So find out sum of all the moment about A to find out EY, Fy find out AY, and Fx to find out Ex because that it pins at E and roller at A. So we have EY equal to 5.50 kips going up, Ex equal to 0. And because that member, so we can make a section cut go through GF, CF, and CD, and consider the right section. So let's make a section cut go through that member, the right section. So we have that here, and we only need to design for GF. So you take moment about C outside of that section. So we have GF have two components, 6 over 6.25, or you can say 12 over 13, and with the moment arm is 8 feet. And then the second component is 2.5 over 6.5 GF, which is the vertical components of the GF. It also counterclockwise, so it will be plus, or you can say 5 over 13 times 6, which is the moment arms, and then the support reactions at EY 5.5 times 12 for moment arm. From that we have GF equal to negative 6.8 kips or in compression. So that member in compression, so it can be buckle. So we have to design for both buckle and yielding. And normally the buckle will govern. So let's start with the buckle, design for buckle. Start with design, because you see problem 4. Okay, of course, buckling. So in that case, as you can see, the equation always the actual less than allowable, less than allowable. And in this case, we already know with the previous worksheet, we are very much doing this one. So we have, what does that mean? In here, the GF, the fourth GF have to be less than or equal to the allowable. In this case, have to be critical, that is the failure, over the factor of safety due to buckle, and the problem gives us the factor of safety equal to 4. So we can plug in this case, pi square E I over KL square, factor of safety for buckle. And as you can see, for we assume the truss is pins at both ends, right? For the truss member, the assumption of the truss is 2 force member pins at both ends. So when it pins at both ends, we have the K equal to 1, right? So from that we can have not pins at both ends for all the truss member. So from that you have K equal to 1. Okay, so that's what we have for K. How about the L? The L of this truss member, as you can see, that is 2.5 vertical and C horizontal is 6. So this member, the truss member of this one, L of GF equal to 6.5 feet. 6.5 feet. So we can plug down in here with all we already know. So we can plug in that equation. That equation become 6.8. As you can see, that is 6.8 kips in compression. So we have 6.8, and we only get the magnitude in this case. Less than or equal to pi square E. It gives us aluminum. It's 10,600 KSI. So we have that here. 10,600 KSI. For the I, for cross section is the circular. If you go to the inside back cover of your book, it will be equal to 1/4 pi over 4. Okay, so we can have that one. Back cover of your book, we have that equal to 1/4 pi r power 4. That is the I for circular cross section. We divide by KL, so we have that is 1 time, we can time for 6.5, that is the length of the GF, 6.5, and then we have to time the 12 to convert to the unit in inches, and then square, and then the factor of safety due to buckling. The problem gives us is 4 and yielding it 1.5, so you can plug in here times 4. From that we have everything is known except the radius. So you have the R4 equal to greater than or equal to, from that one equation, one unknowns, greater than or equal to 2.014 inch 4. From that we can have r greater than or equal to 1.19 inch. And from that we can have the diameter, because the question is determine the diameter, 2.38 inch, and we want to find out what is the next 1/4 quarter inch higher, right? So from that we can choose next one to increment higher. We have to go higher. If we go lower, then it will not be good for the factor of safety that given here. So D basically equal to 2.5 with that increment, 2.5 inches. So that's the design that we need to have for buckling. And now we also do the design for yielding. Okay, so the next step we have design for yielding or crossing. Design for yielding. And in this case, similarly, you have the actual less than or equal to allowable. And for the yield, so we talking about the stress, normal stress. So we will have sigma actual less than or equal to sigma allowable. Sigma allowable. So we can put in here with the equation sigma actual. Basically, it will be equal to the P actual, right? P actual over the areas less than or equal to allowable for yield. So the yield stress, that is the failure level, divided by the factor of safety due to yielding. Due to yielding. So plug in the P actual, basically the actual normal force in that member GF, 6.8 kips. So plug in here, we have 6.8 for the area of circular cross section. So we already know what is the equation with regard to diameter. Let we find out. Here, sigma y for aluminum is 41 ksi. So you can plug in here 41 ksi divided by factor of safety due to yielding. They give us 1.5. From that, we can get the areas have to be greater than or equal to 0.249 inch square. And as you can see, the equation for areas pi d square power 4 greater than 0.249. So from that we have d greater than 0.563 inch. And let's compare to the buckling. We design for buckling. D, we pick D at least 2.38 inch with 1/4 inch increment. We choose D equal to 2.5. Now the design for yielding it D at least 0.563. So as you can see, these two, so you choose with these two, you have to go with the higher. Okay, so you use with that, compare with that. So you choose use from the two, right? You have use D equal to 2.5 inches for circular bar. Because of that, you can choose the next higher here. For this one, it basically equal to 0.75 inch, right? So this compared to these two, we have to select the maximum. So from that, we have to go for 2.5 inches circular bar. And that our design. So that we can box How is that? So go to low, go to Home Depot, do it yourself. Select the aluminum circular bar D equal to 2.5 inches in diameter. Then you can design for this truss member GF and in compression. And as you can see, this in compression, and you see the govern in that case is the for buckling, right? Because the D.25 you need the diameter equal to 2.5 inches for the buckling. Only need 3/4 of an inch diameter for the yielding. So in that case, the buckling govern, if you recall, this member is a long column, right? Long column, if we remember that. So with that, you can see that for the member in compression, it tend to govern by the buckling. For the member in tension, as you can see, member in tension, it never be buckle. It only designed for yielding. The size tend to be smaller. So with that in mind, I go back to your engineering mechanics when we have the truss member in project 1 here. And for this one, as you can see, the with that truss member, you see the top member here, the top member, for example, there, that is the top member. That member is in compression. This member in compression, this member in compression, that tend to be bigger size compared to this member. This member tend to be tension, and it only designed for yielding, and that you can see it's smaller size compared to the top chord in here. And that the concept, the top chord or this chord are in compression. You have to design for both buckle and yielding, and the buckle tend to govern, and that make the size much bigger than the bottom chord. Make sense, everyone? So that's why in the truss you have different size in here when the member is in either in tension or in compression. Use that concept to do for your the design project that we have also initiated today. So that apply, this problem apply for similar concept here to design for your design project with the general program that we introduced. So one step before we finish, that is the actual safety factor, right? Actual factor of safety. So for actual factor of safety, we have for two scenarios. So already now, the diameter we choose is 2.5. So you have the for yields, we have, let's say yield, we have the sigma actual is equal to P actual divided by A, and now the A we already choose, so it's 6.8 kips. That is the actual load on member GF divided by A by D square over 4, and we choose that it's 2.5, so you get it 6.8 divided by 2.5 square divided by 4. From that we can have equal to 1.385 KSI kips per square inch. So the factor of safety, the actual factor of safety due to yielding, okay, it's equal to the failing level, sigma yield, divided by the sigma actual, and that is equal to 41. It equal to 41 divided by 1.385, so that we will get it 29.6 for yield, right? For yield. So it's a lot. Its high factor of safety is a lot for yielding, very high, the actual. Why the original, as you can see, we only set 1.5, and now with the design, it goes to almost 30 factor of safety. Why? Because in this case, if the member in compression, the buckle is governed. So buckle. So we have P critical. We can find out the P critical. P critical, which is P failure. So plug in the number pi square EI over KL square. And we can plug in pi square E 10,600 KSI. And then the I 1/4 pi D R4. So in this case, it will be 2.5 is the diameter. So the radius is 1.25 power 4. For those of you don't know, the I for area moment of inertia for cross-sectional, the circular cross-section, go to the back inside of your textbook, inside cover of your textbook, or go to Canvas. We have that appendix for you. So plug in here. So you have 1 for the pins again. The length, of course, unchanged, 6.5 times 12 inch per foot square. And then time with that, we can find out the P critical, which is the failure due to buckle. That is 32.97 kips. So from that, you have the factor of safety due to buckle equal to P critical due to the P actual, and that plug in 32.97, the actual 6.8. So from that, we will have 4.85 for buckle. We set forth the factor of safety at least 4 for buckle. Now we got 4.85 because we jump a little bit higher in diameters. That makes sense in here. So with that, we done for this problem. And whatever you do for the design project, if you don't know, go back to here for the process to design for compressive member of the truss. For the tension member, go to the member in tension. You can go to lesson 2, and as you can see, we don't need to design for buckle, only design for yielding. With that, we done for worksheet 5D.